Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about DNA data storage. So let's dive right into it. Now we have to understand what is the problem that we are looking into DNA data storage. Well, reality is we are creating data at exponential rate. What does that mean? That simply means our rate of creating data is going exponentially higher. Meaning, if you had bought a camera, a good camera in 2010, let's say, it would have been creating a file, let's say 100 Mbps. Now we have camera that is creating 1 gigabyte per second. So let that sink in. Basically, the amount of data we are creating and the amount of devices that are creating it's exponential. Meaning, if back in the day, 25 GB discs, optical disc was good enough. For example, like Blu-rays, they were good. We were happy about it. This was like, wow, the quality. And to be fair, this still beats any full HD streaming. But it was not enough anymore. Then we went to basically it's a bigger brother, Ultra HD. At HD it's now already updated. So that's the reality of it. We are creating data exponentially harder, faster rate. Meaning we have nothing to store it and nothing to store it long term. Now, how does right now the world's supercomputers, stock markets and all that, basically everything that is backed up, how the heck cloud is quote unquote backed up? Well, it's backed up in something like this, basically LTO tape library. Now, fundamentally, these things are not long term. Like there are disk variant of that, like Sony and Panasonic does make, which is bit more long term, but again inherently not very long term. Basically it's not like how film rolls have backed up. Basically every movie studio right now, once they have finalized the movie, like this is the movie and they have to store it, they make a negative basically a film out of it, and then they store it in a vault, because that puppy will be there 100 years from now. No digital media will be there. So that's the whole thing. And the amount of data rate that we are creating, even these sort of systems are falling apart. They simply cannot back up. There is no way in hell you can back up whole of YouTube. There is nothing that can allow you to do that flat out. And these systems that we are utilizing desperately to keep backing things up, they are active system, meaning they have lot of moving components, things that will degrade and break down, and somebody has to physically be there. There has a lot of power consumption, it has a lot of maintenance, again moving parts and things of that nature, and it also consumes resources. For example, these LTO tapes, while they are amazing, they do survive for 10 years, but that's their maximum life. You're not supposed to wait for 10 years. You're supposed to read it every, let's say, 2 years or every 3 years, and if you find a fault, use another backup tape to restore that data. If you find that tape is not working, you throw it away and replace it with a new one. And every few years, basically generally every 10 years, you transfer all the tapes. Let's say LTO 5 was there when you created it, now LTO 6 or 7 is there, you will move forward to that. So that's how all the servers are backed up right now. It's tedious, it's expensive, it's brutal, and it's very low capacity. Meaning even with huge tape libraries, you are only talking about 1 day of YouTube. So you get that point. It's inherently very low capacity. And we want, in terms of backup, simply we want put and forget and high capacity. Well, we can achieve MDisk supposed to last for 1000 years. Again, 1000 years is good, but not that good, because we have books older than that. So that's not that good. And high capacity, again, even a best M disk you can buy right now, it only goes to 100 gigabyte on the packet, and that's 90 GB of read capacity. That's not that much. And there are some Sony quad layer Blu-ray that is 115 gigs, not too much. So that's the problem. Right now we have no way of backing things up. There is no archive, and we are creating more and more and more and more data. So we are literally running out of space. So somebody had an idea. Now this idea came from basically labs who are tasked with storing human genome project. Now basically they were storing all the data, and then they had an epiphany. It's like, dude, we are storing data of the DNA, which is so huge. Basically, you take a human genome and decode it. It's huge amount of data, and then they are storing it. And it's like, wait a minute, we are storing data of DNA on another medium. What if instead of doing that, we store the data of DNA onto DNA itself? That's the epiphany. It's like DNA has the data, we are extracting it. What if, again, extracting it was awesome for temporary and study and all that jazz, publish it and all that jazz, but after that, for storing, rather than using hard drive, just store it in a DNA. So that's the light bulb moment. Now the reason why it is even feasible to do is the same reason why nature does that, is DNA is digital. Meaning DNA, if you look at it, it does have different elements. For example, phosphor, carbon, nitrogen, oxygen and hydrogen. It does have all these puppy, but they are in discrete states, meaning you cannot mess this up. Analog always have that, is it the signal messed up, or is the data in that messed up? That's always the issue with analog systems. They are always messy. Digital is either it's on, either it's off. Same goes here. It has 4 such states, meaning either it's C, either it's G, or either it's A, or either it's T. You will never mix them up. That is very desirable for quality data storage. The basically discrete state, basically you cannot mess this up. And even if you have a, let's say, chain, the chain has a pattern to it. Basically you cannot like if they're supposed to be A, you know they're supposed to be A, because like how other basically other molecules are align themselves. Like there is a inherent pattern limiter. That's why nature uses, that's why this is so amazing. And DNA is one of those things that we know for a fact that is time tested. We have been finding an intact DNA of ludicrously long time, as in like, yeah, for millions of years and millions of years. And technically speaking, we are made out of DNA, and we have like almost same quote unquote same CGAT as dinosaurs. So you, of course, arrange it in a different manner. That's why you are not a dinosaur. So that's the whole point. It is one of those things that is time tested in terms of just like randomly finding fossilized DNA. And that's why I specified there is a pattern to this. You cannot just like have random things in there. There is a pattern to that. If you know that pattern, you can recreate even a damaged DNA. We know for a fact that millions of years can be handled with this sort of thing. Now, of course, there is an inherent physical limitation of any storage medium. For example, if you are trying to store data on this sort of thing, and you're like, hey, I'm gonna be awesome about this. Here's there is a phosphorus in that does not have a very long half-life, meaning it will decay. Other things will also decay: hydrogen, oxygen, nitrogen, carbon. Of course they will decay at different rate, but once you have, like, let's say phosphorus starts to decay, it starts to become vulnerable. Now be mindful, compared to everything else we are utilizing, this is like put and forget for 10,000 years. And of course you will do some other backups, which we will talk about after that. So where we are storing the data, we are storing the data in molecular chains, meaning how these things are arranged, basically how C, G, A, T are arranged in a chain. That's the critical aspect. The C, G, A, T itself does not store too much data. It's almost like how CD, you may think CD or DVD or Blu-ray or anything is like, the pits and LAN are 0, no, it's not. It's like how they are changing. Basically, if it's going from pit to LAN, that encodes 1, a LAN to pit, that changes, encodes 0, things like that change. So basically this chain is the data point, and it's very small. To give you an actual real world context of that, if you take that strand and you want to measure it up, this is barely 2.5 nanometers. This puppy is tiny, like ludicrously tiny. I mean, like, our modern CPUs have not reached yet. And be mindful, when we are talking about CPUs, all they have is like on or off. This has 4 discrete states, so it's fundamentally very tiny, and you can make them in principle very long. And what will happen if you make them ludicrously long? It will carry, like, whole YouTube in a very few grams. You don't have to worry about it. It's like, in terms of density, it's on a god tier. I'm like, that's why nature uses that. Think of it this way: every single DNA data point that is needed to create you, basically to make you, it's in every single cell. Every single cell is, yeah, I got this, man, I got this, I got the whole data, don't worry about it. That's the amazing part of it. So that's the idea. So how the heck it's gonna work? Well, you have to understand, we have to create a new kind of code. It happens with every time a new physical media is created. You have to utilize that media accordingly. For example, CD, it has a quote unquote base encoding layer. Same goes here also. So you will take your binary data, and then you're gonna create a base 3 code. For example, I'm taking base 3 encoding, and it will allow you to have basically 4 states. You want to utilize that. For example, A will be encoding 0, 0, G will be encoding 0, 1, C will be encoding 1, 0, T will be encoding 1, 1. Now you have to utilize that in such a way that you have lot of error correction. Be very mindful. DNA is awesome, but it does suffer with lot of consequences. And engineering first rule: complexity is the enemy of reliability. And DNA is idiotically complex. So how does DNA manage that? It does not. It has a lot of decay. So it has replication, backup. Basically, it's actively doing what LTO tapes are doing right now. Basically, we are keep going, copying and double checking. That's how our DNA deals with it. It's like, it knows for a fact that you will try to copy it, there will be some error, then some other molecules will come. It's like, hey, you're wrong, done. So that's how you have to put that into account. That DNA, even if you think that you have made it correctly, you may have a what we call a write error. So lot of error correction has to be embedded into the system. Basically, binary files to the base encode, that encode itself should have a system where it's like, if you are reading the DNA, if this puppy is not done correctly, you will have a scenario where it's like all the data would be either jumbled up or corrupted beyond usable data. So it must have lot of error correction, basically bigger brother of ECC RAM. Same. Now be mindful, it's not a new thing. It has been done for CD, it has been done for DVD, it has been done for Blu-ray. So it's one of those things that it's done in your hard drives. The hard drive also tries to error correct everything. And it also need indexing, because yes, in principle we can make ludicrously long artificial DNA strand. Right now we do not have that luxury. So right now we are making DNA basically fragments. So the protocol creates in such a way that, like, it creates packets, quote unquote, and those packets are created into fragments, and it repeats so often that even if you have like one fragment DNA, you should get that, because that should repeat 4 times. So no, as in like 4 fragments would be copy of each other. So no matter what happens, you should be able to retrieve the data, and we can make them into very small strands. So that's, again, longer strands are more vulnerable. And again, we have not figured, it's like almost carbon nanotube. In principle we should be able to make them hundreds of kilometers long, but we only able to make micrometers long. That's the thing here. And how the heck you gonna quote unquote write? Well, you're gonna use synthesizer, meaning you're gonna have mixer that's gonna mix A, G, C, T in the ratios that you want, basically the ratio that your base 3 encode is gonna provide. And then how the heck you're gonna read it? You're gonna send that data to sequencing machines, and because of Human Genome Project, these sort of machines are surprisingly common. So the final data will not be readable unless you have this base 3 encode. Be very mindful of that. This is one thing you have to understand. Just because you can store data into DNA does not mean you can read it. This thing is the very critical key, basically. So yes, you can have a scenario where you stored all the data into a DNA. Yes, in the future somebody can retrieve that data, but yes, they may not be able to read it. Think of it this way: let's say you do not know Mandarin and somebody wrote the instruction manual in the Mandarin itself. You're not going to be able to use it. Same thing happens here. So this base 3 code must survive independent of the DNA system, because this cannot be encoded into data itself. You cannot code how to read a CD in a CD. You have to have some other sort of system there. So that's the whole thing. Base 3 must survive. So this T, C, 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 T, H, C, G, G, A, T, this all sort of system will allow you to encode large amount of data, and you will have lot of error corrections. You will have lot of system that will in place that will check for errors and will allow you to have good basically confidence when you are retrieving the data. Yeah, I'm retrieving the actual data. So that's the working behind it. Not demo. Has somebody actually did that? Well, here's the deal. It's kind of old technology at this point in time, 2022, so to say. So if you have money around $7,000 to $10,000, you can pay for it. And people have done that. People have done that for Bitcoin wallets, where they're like, and people have suffered, like, Bitcoin value went up, and some people have lost their hard drive. They had only one copy of that wallet, and poof, millions of dollars, poof. So they're like, yeah, $10,000 it's acceptable. So they're like, creating that data into DNA. Now be mindful, they're asking a lab to do that, and no lab right now, of course these labs will do that, but like they're not built for it. It's almost like, yeah, we'll do it, extra money, who never hurts. So they will do that, and when you have to retrieve that data, you have to send it to another lab to sequence it. So be very mindful. Lab will make the DNA synthesis, and reading destroys the data. This is one of the things. It's not like a CD where it's like, warm drive or DVD, warm drive or Blu-ray. It's like, you write once, if you try to read it, basically the synthesizer sequencing machine is inherently destructive to the DNA. It's going to destroy it. So the data will be destroyed. So you must create clone of that DNA. Now you're like, wait a minute, creating DNA is difficult, and now you're talking about like every time I try to read it, I'm destroying it. Thankfully, that's not an issue. Right now we have enough understanding of microbiology that cloning is super easy. Like in all this step, basically creating the encode, creating the synthesis, and then try to read and error correct and everything, all these things are hard. Cloning, that's easy. That's like, you don't think about it. It's like, just take a vat which has the right growth medium, put your desirable basically microorganism, tada, Control Z, Control V, millions of times. You don't have to worry. It's like you can keep bad reading, have a bad synthesizer and go through hundreds of copy, and you still have millions of copy left. So that is one good thing about this DNA system, and that's why I specified there is a limit to how long DNA will last. You're supposed to, like, every, let's say, 10,000 year or every 1,000 year, you're gonna take that, replicate it again sometime, double check that data is there completely intact, and then you store it again for 10,000 years. You have to do that. Otherwise, if you only have, let's say, a few strands, every time they are trying to read it, that data would be converted from DNA to something else, and then you have to hope that they have something else to back up for a long time, eternity, so to say. So DNA cloning is surprisingly easy, and the first demo that was actually done was only few megabytes, like 2 megabytes if I'm not mistaken. And then they started to push forward with that. June 2019, they achieved a surprisingly big milestone of 16 gigabytes of Wikipedia was stored. And right now, you have to understand, this is experimental technology. Microsoft is very ahead in this. Not ahead as in, like, of course they are talking about it. Other companies may be working in the background and not talking about it, though maybe they are ahead or maybe they are behind, I don't know. Right now, if you type DNA, Microsoft is the first first company that keeps popping up, simply because they are pouring a lot of money and they are kind of doing it as an open source system. Because yes, it is true, like we have to figure out a way to store our DNA data. DNA data, I'm talking like data. And one person said something very amazing. It's like time is the one that tells you which data is important and which is useless. So you have to store almost everything if you really want to archive humanity, so to say. So this is one of those things that we have to sort. And this machine that you keep type any system, you're gonna find this machine. The trick with this is like all the steps, meaning send data and extract data, all the step is done in this one thing, and this is very slow, as in bits per minute. For example, your dial-up modem is faster, multiple times faster than this puppy. Then you're like, what's the point of making this? Well, the idea is if they compactify everything, basically think of this way, like why we did not have DVDs before CDs. Somebody had to lay it down, like this is good enough, let's start with this. Somebody did that. Then we had DVD, then we had Blu-ray, then we had quad layer Blu-ray. So Microsoft is trying to do that. It's like once they show that this can be done, again hundreds of engineers like I can improve it this way, I can improve it that way. Like hundreds of engineers will look into it, they will try to process it, and then it's going to start better. But we must have that first CD moment. Basically, when we had CD, only then we now live in a world where you can actually buy discs that are like 115 gigabytes, or like archive grade discs that go up to 300 gigabytes in one disc, and they come in cartridge. That cartridge is like 5 terabytes. So you must have that first step. This is that first step, basically everything being automated, quote unquote, where you like computer. You don't have like, okay, I need to have a PhD thesis in biology in order to deal with this. So that is the whole point. Right now we do not have finalization, nor we have standardization. I specified this very carefully. Do understand this. You can store your data, but does not mean you can decode it properly unless you have the encoding protocol survive independent of DNA. So let's say in future, let's say humanity went into stone age and we started to recover and we started to build our civilization, and we figured out DNA, and we started to DNA archive. Like let's say that part we figured out, like these are artificial DNA and it has the data. Nobody will be able to read it. Like they will be able to extract data out of it, but that data will be jumbled because we do not know how the heck it was encoded. This is a very critical aspect. Now, of course, maybe you have 10,000 supercomputer crunching all the possible variables and you're like, hey, this image makes sense. That then you can, backtrack it, but that's a very difficult aspect. So it's not as amazing as you will think. And not to mention, you still have to clone it. And DNA itself is very fragile inherently. The only reason we are thinking about DNA being very long-term stable is like if you can put in cold, a dark place, nothing in itself, it's not demagnetizing, and it does not have the size limitation of basically optical discs. It can be just like put it there, forget about it. And again, if it is cloned millions of times, at least one copy will survive just by sheer mathematical luck. So what we can expect in the future? Right now, the biggest advantage of this sort of approach is that it will never become obsolete. Now, that is the one thing that I really liked about the engineers and scientists who are working on this. Like, as long as we are human, as long as we are advanced enough and capable enough, we always gonna have to. It's not optional. We have to study our own DNA. Meaning, as long as we have advanced biology, we're gonna study ourselves. This pandemic taught us, like we created vaccines utilizing what? DNA. The understanding of DNA, RNA, and all those things simply means you're gonna always have a tool that can read, basically quote unquote, analyze a DNA. We're always gonna have that. And right now, we have a technology like this pen drive that can read DNA. So this is very advanced. This all happened simply because of Human Genome Project. So before Human Genome Project, this was one of those ironic projects where it's like boatload of money was poured into it, a lot of scientists, and everybody was like, oh, it's gonna be over budget, it's gonna behind schedule, and it turned out under budget, before schedule, because they kept developing better tool. It's like, oh dude, who cares, do it on the side. That's how amazing this was. But all that data aside, we still need exponential growth. Right now we are in bits per minute, not good enough. And not to mention $7,000 to $10,000 to store like few megabytes of code key, not really that useful. We need to be exponentially much better. Basically, how CD went from 700 MB to DVD to 4.8 gigabyte to dual layer DVD to 8 gigabytes. Then we went to Blu-ray to 25 gigabytes, dual layer to 55, and then to 100, and we went multiple of ahead. We have to do the same thing here. Same with hard drives. So we started with megabytes hard drive, now we have terabytes. So same thing has to happen here. Right now we are not there yet. Flat out, we are not there yet. And read, write speed both have to improve. At least write speed, so you can at least back up. Basically, think of this way: like if YouTube is creating 1 terabyte per second, you must be able to write it at higher speed than that. Otherwise, you will be like, yeah, we are backing up YouTube, yeah, and YouTube died. we could not had enough time to back it up. So that's why write speed is really important. Read speed, you could have a bit more luxury, but write speed must be better than this. So it must become cheaper, and it's very specific tool. It's specifically for archival storage. Do not expect this to become your server. This is not for that. It's inherently, nobody is even planning for that. It's just people getting a bit more creatively emotional and getting carried away. But this sort of system is not gonna suit in your server. And like the best you can have, like in the future, you can have like a how tape drive is, like, yeah, or this DNA file, I'm gonna put that, it's gonna destroy the DNA and it's gonna restore the system. That's the best you can expect. Do not expect your hard drives to be replaced by DNA system. All the capacity benefits does come with serious side effects. So that side effect is basically ludicrously slow read and write. Some people are working on system that should allow them to do what we call a random access on this, but again, very early on, and even that random access is like, yeah, very slow. So fundamentally, this is a very amazing feature. If we crack it, it does have the option of having truly long-term archival storage, and if we can figure out a way of, like, making sure that encoding method is preserved also with it, we're gonna be safe for a very long time. Now be very mindful, this will never replace your flash storage. Do not get carried away. I've seen some people who are talking like, oh, what if we have like a sugar cube in our camera and be like, millions of gigabytes in capacity. Yeah, that's not happening. That's not happening. So this is amazing technology, and I really like the fact that that's the first thing they thought of. It's like, hey, DNA will never be obsolete. We've been studying DNA in 1970s. We are still doing it, and we will be doing it. So that's the amazing part of it. So this was my presentation on basically DNA data storage. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. I would urge you to leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.